technology. In this lecture, I want to discuss the several applications of solar energy. The today's topic is the solar air heating system, solar water heating system, solar distillation, solar cooker, solar heating and cooling of the building, and the other applications. First, what is the solar air heating system? The solar air heating system is basically a large collector area that is heated by the solar energy and a large volume of air that is moved over the collector system. The air can be moved directly into the home for heating or over a storage medium that will increase the temperature of the storage material so that the heat can be removed at a later time. The air heating system can be designed to heat any individual room or the entire house. Certain materials that are used in the home may increase the efficiency of the systems, such as a large mass of concrete or the masonry products that tends to heat up more easily and hold more heat energy over longer periods of time than do carpenting and the wood structure. How the solar air heater works. The thermosiphon collector consists of clear corrugated polycarbonate panels fastened to 2 by 6 inch studs, which are shown in the figure. The collector is glazed with clear sun-top corrugated polycarbonate panels. The manufacturer applies an ultraviolet resistant coating to the panel's sun-facing side to extend their life. A couple of variations could improve the system's performance. Substituting the dual-wall polycarbonate glazing for the single corrugated sheet would reduce the thermal losses through the glazing, although some loss in the energy absorption also will occur. This type of glazing, which consists of two sheets of polycarbonate separated by the supports waves, also simplifies the installation since it requires the less support and does not have the corrugated edge that require the sealing. Buildings in cold climates will benefit the most from this change, which would increase the cost by around $100. Another option is alternating the collector panels and windows on the south wall. This approach would admit the more light and some direct heat gain through the windows without the glare, high losses, and overheating that accompany full window walls. In altering the collector's design or alterning the collector's design, make sure you don't violate these guidelines. Number 1 is the collector's depth should be at least 1 by 15 its height. The absorber must offer low resistance to airflow. The vent area should be at least 50% of the collector's horizontal cross-sectional area. The air path through the collector should be unobstructed and run the full length of the collector. This should be followed as the guidelines. The collector frame is built of common dimension lumber and consists of vertical members, a bottom sill and a top sill. One is bottom sill, another is the top sill. So 2 × 8 top sills slope to the said rain, which is shown in the figure, and the bottom sill is 2 cross 6. The bottom sills are there, which are shown in the figure. Now the bottom sill is a 2 by 6 and a 2 by 8 is used for the top sill, which is shown in the figure. The collector frame components are attached to the building with lag screws driven into them from the inside. The clear panels admit sunlight, and an absorber suspended inside the collector captures the sun's heat energy. The air around the absorber warms, expands, and rises, creating a convection current, which are shown in the figure as the arrow. Now the absorber, a black metal window screen, is installed on battens fastened vertically to the uprights and across the top and bottom of the base, about halfway between the glazing and the sheathing. After measuring the thermal performance with 1, 2 and 3 layers of the screen, it is found that 2 layers work best. Vents at the top and the bottom of the collector allow the air to circulate through it. The top and the bottom vents are simply the holes cut through the building's sheathing and sheathing. Cool air enters the lower vent from the interior as shown in the figure, is heated by the absorber, rises to the upper vents and returns to the interior. Air circulation continues as long as the sun shines on the collector. At night, the airflow reverses as air in the collector cools to the outside temperatures. Simple plastic flapper valves on the top vents stop this reverse circulation and keep the heat inside, which are shown in the figure as the upper portion. The flapper valve is there. Now, how much heat can solar air heaters provide? That depends on a lot of variables like the solar panel size. This will determine the volume of air we can condition and the output temperature. Choosing what size to build or buy will depends on our needs and how much exterior wall space we can dedicate to a panel. Second is the solar absorption. Panels are limited in how much heat they can collect depending on how reflective the black surface is, and we will do better with a matte paint than the glossy. Glazing will instantly reflect about 10% on its own, but is essential especially in areas with air movement creating a wind chill factor in winter. So really the best we can hope for in overall performance from a solar air heating panel is about 80% absorption of available light. Third one is the heat panel conductivity. The materials with the higher conductivity will improve the solar air heater performance. The black PVC pipe, for example, would not provide as much heat as a black metal pipe. So we should use the black metal pipe. Even different metals will have the different rates of conductivity. Copper is one of the best conductors, but it is very expensive and can be tricky to get in larger diameter or to get the paint to adhere to. So the advantage of increased conductivity would likely not be worth the added cost. To choose the downspout panel option for a dye solar air heater panel build, be sure to use the metal and not plastic. And if it has a glossy finish, then it would be worth it to paint it matte black. Fourth one is the home performance. How much heat a house needs to keep occupants warm is determined by the how much it loses. A solar heater will provide a greater percentage of the required heat in a home if that heat demands in lower. So how well insulated and airtight a house is will be a deciding factor on how big the passive solar air heater needs to be to make a difference. Next one is the cloud coverage. In areas that are regularly overcast, it may not be worth the cost and hassle to either buy or build one. Certainly, the payback period for labor and money invested in a solar air heating panel would be much longer. Latitude. The further north you go, the less sun hours you will have a winter's day, so the cost or effort required to make a panel will stop being worthwhile at a certain higher latitude. Now the second application is the solar water heater. Direct and indirect hot water systems. There are several different ways to heat water for use in the home. Solar water heating systems that use the flat plate solar collectors to capture the sun's energy can be classed as either direct or indirect systems by the way in which they transfer the heat around the system. In order to heat your water successfully and use it during both the day and the night, you will need to have both a solar collector to capture the heat and transfer it to the water, and also a hot water tank to store this hot water for use as needed. A low voltage 12-volt pump can be used, which can be powered by a small photovoltaic cell or electronic controller, making the system greener. Direct systems are usually used in warmer climates with few cold days, or is drained in winter to stop the water in the pipes from freezing. Chemicals cannot be added to the water for protection, as the same water that circulates through the flat plate collector is used in the home. Now, a direct solar water heating system, also known as an active open loop system, use a pump to circulate the water around the system. The cooler water is pumped directly from the home to a central water storage or immersion tank and passes through the solar collector for heating. The hot water leaves the flat plate collector and returns back to the tank, flowing in a continuous loop. From there, the water is pumped back into the house as hot usable water. In a passive direct hot water system, the system does not use the pumps or control mechanisms to transfer the heat created to the storage tank. Instead of passive systems are what are called the open loop systems, which use the natural force of gravity to help the circulate the water around the system. Now this type of system which is shown in the figure, that is the solar flat plate collector combined with a horizontally mounted storage tank to some kind located immediately above the collector. The water heated by the sun rises naturally using the convection through the solar collector's pipes and enters the storage tank situated above. As the heated water enters the storage tank above, the cooler water is forced out and flows down to the bottom of the collectors, aided by the gravity, as cold water is more dense than the hot water. So this cycle of the hot water rising and the cooler water falling is known as the thermosiphon flow, and the continuously repeats the unaided while the sun is shining. Now the thermosiphon hot water system is the most common type of solar heated hot water system on the market, and most commercially available the passive direct solar hot water systems use this type of roof mounted flat plate collector and the storage tank combination as shown in the figure. However, care must be taken when the installation of such a system, as the combined weight of the solar collector, storage tank and the water itself may be too much for the design of the supporting roof. So-called remote thermosiphon system works on the same principle as the previous passive direct thermosiphon system, except that the storage tank is located away within the roof space or the void, dissipating the weight over a larger area and also protecting the storage tank from the cold weather and the temperatures. However, for the thermosiphon process to work correctly, the base of the water storage tank must be situated at least 1 to 2 feet above the top of the flat plate collectors. This distance is also known as the system head height. Now, indirect hot water systems. Indirect hot water systems, which are also known as the closed loop systems, differ from the previous thermosiphon system in that it uses a heat exchanger which is separate from the solar flat plate collector to heat the water in the storage tank. Indirect hot water systems are active systems and require the pumps to circulate the heat transfer liquid around the closed loop system from the collector to the heat exchanger in the tank. In the heat exchanger, this is a insulated storage tank where the circulating pump is attached to it, and the hot water is entering into this heat exchanger system, and the cold water will be the outlet of this system. The system contains an antifreeze solution, typically a 50% of glycol or the water mixture in the primary closed loop instead of just water which is heated and is kept separate from the main domestic hot water supply. The heat exchanger transfers the heat from the collector's antifreeze solutions to the water located in the water storage tank, which is shown in the figure, the antifreeze solution in the closed loop. The heat exchanger can either be a copper well inside the lower part of the storage tank or a flat plate exchanger outside the storage tank. The system is also likely to be more efficient, and the hot water storage tank can be placed anywhere in the home because it does not need to be higher than the collectors as in the previous passive or the thermosiphon systems. One of the main advantages of this closed loop indirect heating system is that the antifreeze solution gives all year-round operation in areas where the temperature falls below the freezing point, as well as protecting the system from corrosion of the collectors by untreated tap, water containing gases and the various dissolved salts. The main advantage of a forced circulation indirect hot water system is that an existing domestic water heating system can easily be converted to solar heating of the water just by adding a flat plate collector and a single pump, as most homes use the gas or well fire boilers as well as a hot water storage tank with built-in heat exchanger well. One disadvantage is that, however, is that the closed loop system is dependent on electricity for the circulating pump, which may be expensive or unreliable. Some designs use a small low voltage pump and photovoltaic panel alongside the collector, making the system more efficient and greener. For larger installations and in cooler climate, the hot water tanks are included below the roof within the buildings. So forced circulation indirect solar water heating is the norm. Now the solar distillation. The solar distillation is the use of solar energy to evaporate the water and collect its condensate within the same closed system. Unlike the other forms of water purification, it can turn salt or brackish water into the fresh drinking water. The structure that houses the process is known as a solar still, and although the size, dimensions, materials and configuration are varied, all rely on the simple procedure wherein an influent solution enters the system and the more volatile solvents live in the effluent, leaving behind the salty solute behind. There are many variations on the theme of the typical single slope or basin still, and these can fall into one of two categories, active or passive. These levels classify the still by the method it uses to acquire the energy to drive the evaporation of the water. Passive solar stills are of course more conventional and have been the only ones discussed up to this point. Active stills, however, can obtain the waste heat from a myriad sources. A good insulator is necessary to reduce the thermal losses and prolong the evaporation process even into the night. Insulation that could be used include the things like styrofoam with a polypropylene cover or wool. The passive solar stills, this is the conventional stills, rely solely on the sun to distill the water. However, their complexity could still reach that of active stills, if not other more intricate the desalination methods. Conventional solar stills rely solely on the sun to distill the water. However, their complexity could still reach that of active stills, if not other more intricate desalination methods. Passive steels then vary widely due to this one constraint and can be further organized into the subclasses. Some common types of passive solar steels include single effect, multi-effect, basin, double slope, wick, multi-wick, diffusion, greenhouse. The single effect steel are the simplest and most common since only one interface is necessary to convey the energy and collect the condensate. An example of a crucial design challenge in all solar steels is keeping the distiller airtight. If not airtight, efficiency drops severely. Often a shallow trap is used, painted black and flooded. A slanted pane of glass covering allowing condensed water vapor to slide down into an output channel. Another approach is the molded plastic, such that the water cone, which this has the advantage that it is can be more easily made airtight, and mass production should make it affordable. The multi-effect steels require double the effort in regards to ensuring tight seals and could be more too difficult to clean, but they can raise the production of fresh water significantly. The way by which the water is stored for its time in the liquid phase can also contrast. Basin type of steels contain the water in an impervious material that is a component of the entire enclosure and are the most ubiquitous. Wick steels use the cloth-like materials that use the capillary action to propagate the water through the system. When the efficiency and effectiveness are the key, wick steels outproduce the basin steels due to the greater surface area of the evaporation, lower energy cost to heat the water, and the ability to create a much larger effective area for the solar radiation to transfer the energy into the water. The multi-wick steels obviously play off of the typical wick steels, and much like the multi-effect premise from the above, they greatly increase the productivity for increasing the influence surface area exponentially, which is shown in the figure. The diffusion type of steels run with the ideas introduced by the multi-effect and the wick steels and a further advancement to both, which consist of a series of closely spaced parallel partitions in contact with the saline soaked wicks, have great the potential because of their high productivity and density. The seawater greenhouse, which is shown in the figure. The seawater greenhouse marry the concept of solar distillation with the more prominent greenhouse premise. They are neutral because the energy that goes into create the fresh water, even if active, pays off by the freshwater's invaluable quality to grow the plants that promote the evaporative cooling of the air inside, which ultimately carries the active solar steels. These distillers use the additional heat resources to promote the existing thermal processes. The foundation of the design of these desalters has already been laid in the above section. So the sources involved with this branch of solar steels will be discussed with the brevity. The CPC, that is called the compound parabolic concentrators, flat plate collectors, solar heater, novel washed heat, such that the vehicle radiator. The active steels add another element of complexity to the not so complex base design. but once again this alteration can promote faster and larger quantities of the freshwater generation. Now another application is the solar cooker. A solar cooker is a device which uses the energy of direct sunlight to heat, cook or pasteurize the drink and the other food materials. The solar cooker is shown in the figure. The many solar cookers currently in the use are relatively inexpensive, low-tech devices, although some are as powerful or as expensive as traditional stoves. And advanced large-scale solar cookers can cook for hundreds of people because they use no fuel and the cost nothing to operate. Many non-profit organizations are promoting their use worldwide in order to help reduce the fuel cost and the air pollution and to slow down the deforestation and the desertification caused by the gathering firewoods for cooking. Food is prepared as if for an oven or stove top. However, because the food cooks faster when it is in the smaller pieces, food placed inside a solar cooker is usually cut into the smaller pieces. For example, the potatoes are usually cut into the bite-sized pieces rather than the roasted whole. For very simple cooking, such as melting the butter or cheese, a lid may not be needed and the food may be placed on an uncovered tray or in a bowl. If several foods are to be cooked separately, then they are placed in different containers, as shown in the figure. The container of food is placed inside the solar cooker, which may be elevated on a brick, rock or metal trivelt or the other heat sink, and the solar cooker is placed in the direct sunlight. Foods that cook quickly may be added to the solar cooker later. Rice for a midday meal might be started early in the morning with vegetables, cheese or soup added to the solar cooker in the middle of the morning. Depending on the size of the solar cooker and the number of quantity of cooked foods, a family may use one or more solar cookers. The cooking time depends primarily on the equipment being used, the amount of sunlight at the time, and the quantity of the food that needs to be cooked. The air temperature, wind, and the latitude also affect the performance. Food cooks faster in the 2 hours before and after the local solar noon than it does in either the early morning or the late afternoon. Large quantities of food and food in large pieces take longer to cook. As a result, only general figures can be given for cooking time. With a small solar panel cooker, it might be possible to melt butter in 15 minutes, to bake cookies in 2 hours, and to cook rice for 4 people in 4 hours. With a high-performing parabolic solar cooker, you may be able to grill a steak in minutes. However, depending on the local conditions and the solar cooker type, these projects could take half as long as twice as long. It is difficult to burn food in a solar cooker. Food that has been cooked even an hour longer than the necessary is usually indistinguishable from the minimally cooked food. The exception to this rule is some green vegetables which quickly change from a perfectly cooked bright green to olive drab while still retaining the desirable texture. The most foods such as rice, the typical person would be unable to tell how it was cooked from looking at the final product. There are some differences, however the bread and the cakes brown on their tops instead of on the bottom. Compared to cooking over a fire, the food does not have a smoky flavor. Now come to the working principle of the solar cooker. Concentrating sunlight. A mirror surface with high specular reflection is used to concentrate the light from the sun into a small cooking area. Depending on the geometry of the surface, the sunlight could be concentrated by several orders of magnitude, producing temperatures high enough to melt salt and metal. For most household solar cooking applications, such high temperatures are not really required. Solar cooking products are typically designed to achieve the temperatures of 65 degrees centigrade to 400 degrees centigrade for grilling or the searing temperatures on a sun. Converting light energy to the heat energy, the solar cookers concentrate sunlight onto a receiver such as a cooking pan. The interaction between the light energy and the receiver material converts light to heat, and this is called the conduction. This conversion is maximized by using the materials that conduct and retain the heat. Pots and the pans used on solar cookers should be matte black in color to maximize the absorption. Trapping the heat energy is important to reduce the convection by isolating the air inside the cooker from the air outside the cooker. Noted that all figures described are simply energy flow charts and are not meant as the hydraulic systems. For instance, the heat source or the sink, which is an important component for any type of heat pump or chiller, has not been displayed. So the electricity consumption of all the components, that is the pumps, control units and the corresponding connections to the grid, is not shown for simplicity. Now the other applications, that is the crop and grain drying. Using the sun to dry crops and grain is one of the oldest and mostly widely used applications of the solar energy. The simplest and the least expensive techniques is to allow the crops to dry naturally in the field or to spread grain and fruit out in the sun after the harvesting. The basic components of a solar dryer are an enclosure or shade, screen drying trays or racks, and a solar collector. In hot, arid climates, the collector may not even be necessary. Crop and grain drying, the southern side of the enclosure itself can be glazed to low sunlight to dry the material. The collector can be as simple as a glazed box with a dark color interior to absorb the solar energy that heat the air. The air heated in the solar collector moves either by natural convection or forced by a fan, DC fan, which is shown in the figure, up through the material being dried. The size of the collector and the rate of the airflow depends on the amount of material being dried, the moisture content of the material, the humidity, humidity in the air, and the average amount of solar radiation available during the drying season. There is a relatively small number of large solar crop dryers around the world. This is because the cost of the solar collector can be high and drying rates are not as controllable as they are with the natural gas or the propane power dryers. Using the collector at the other times of the year, such as for heating farm building, may make a solar dryer more cost effective. It is possible to make small, very low cost dryers out of simple materials. These systems can be useful for drying vegetables and fruit for home use. The disadvantage of these methods is that the crops and the grains are subject to damage by birds, rodents, wind and rain, and the contamination by the wind-blown dust and dirt. More sophisticated solar dryers protect grain and fruit, reduce losses, dry faster and more uniformly, and produce a better quality product than the open air method. Now the solar energy applications for agriculture. Natural ventilation levels during the summer month depending on the region and weather. Solar water heating can provide the hot water for pen or equipment cleaning or for preheating water going into a conventional water heater. Water heating can account for as much as 25% of a typical family's energy cost and up to the 40% the energy used in a typical dairy operation. A properly sized solar water heating system could cut those costs in half. There are 4 basic types of solar water heater systems available. These systems share 3 similarities: a glazing, typically glass, over a dark surface to gather the solar heat, 1 or 2 tanks to store the hot water, and associated plumbing with or without pumps to circulate the heat transfer fluid from the tank to the collectors and back again. Drain down the systems pump water from the hot water tank through the solar collector where it is heated by the sun and return to the tank. Valves automatically drain the system when sensors detect the freezing temperatures. Drain the back systems use a separate plumbing line filled with fluid to gather the sun's heat. These systems operate strictly on gravity. When the temperature is near freezing, the pump shuts off and the transfer fluid drains back into the solar storage tank. Antifreeze closed loop systems rely on an antifreeze solution to operate through the cold and winter months. Antifreeze solutions are separated from the household water by a double-walled heat exchange. Breadbox batch systems are passive systems in which the storage tank also functions as the collector. 1 or 2 water tanks painted back are placed in a well insulated box or the other enclosure that has a south wall made of clear plastic or glass and tilted at the proper angle. This allows the sun to shine directly on the tank and heat a batch of water, as insulated cover can provide the freeze protection. The solar electric or the photovoltaic systems convert the sunlight directly to the electricity. They work any time the sun is shining, but more electricity is produced when the sunlight is more intensive and strikes the PV modules directly. They can also power an electrical appliance directly or store the solar energy in a battery. In areas with no utility lines, the photovoltaic systems are often cheaper and require less maintenance than the diesel generators, wind turbines, or the batteries alone. And where the utility charge for the new lines, a PV generating system is often much cheaper for the landowner than paying for a new line. The photovoltaic allows for the production of the electricity without noise or air pollution from a clean, renewable resource. A PV system never runs out for the fuel. Solar electric power comes in very handy on farm and ranches and is often the most cost-effective and low-maintenance solution at the locations far from the nearest utility line. The photovoltaic can be used to power lighting, electric fencing, small motors, aeration fans, gate openers, irrigation valve switches, automatic supplement feeders, etc. Solar electric energy can be used to move the sprinkler irrigation systems also. The photovoltaic systems are also extremely well suited for pumping water for the livestock in remote pasture where the electricity from the power lines is unavailable. Photovoltaic is often much less expensive than the alternative of the extending power lines into these remote areas. So this is the all about the solar energy, renewable energy sources, their applications, their storage systems, and on working principles of the solar energy sources. That's all. These are the references from where I make these tutorials. You may go through these references to learn more. Thank you.